Hi, and welcome to the fourth lecture of machine learning course. In this video lecture, I'm going to talk about convolutional neural networks. You may have noticed that the number of parameters that a feed-forward network can have grows very fast as you make your network bigger. To put it more into perspective, if you add another 1000 unit layer to an existing neural network, then you add more than 1 million additional parameters to your model. And the fact is, optimizing such big models is a very computationally intensive problem. When our training examples are images, for example, the input is very high dimensional, and if you want to learn to classify images using feed-forward network, then the optimization problem is likely to become intractable. A convolutional neural network, in short CNN, is a special kind of feed-forward neural networks that significantly reduces the number of parameters in a deep neural network with many units without losing too much in the quality of the model. CNNs have found applications in image and text processing where they beat many previously established benchmarks. And because CNNs were invented with image processing in mind, I will explain them on the image classification example. But keep in mind that they have found their ways to many other application fields. So if you understand the architecture behind the convolutional neural networks, how it works, what is it that it tries to optimize as, then you very easily can use it in many other forms of the problems. So let's first see what is the intuition behind a convolutional neural network. You may have noticed that in images, pixels that are closer to one another usually represent the same type of information. Here, for example, you can see a sky, water, leaves, a flower, and so on. They are similar in pixel. The pixels are close to each other, representing these things. But there's an exception. The exception from the rule are the edges. Some places like this. And these are the part of the image where two different objects here, like the leaf and the water, touch one another. And if we can train the neural network to recognize regions of the same information as well as the edges, this knowledge would allow the neural network to predict the object represented in an image. For example, if the neural network detected multiple skin regions, some like here, 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 and here, and the edges that, for example, here look like an oval with a skin-like tone on the inside of a bluish, I don't know, tone outside, then it is likely that it is a face on the sky background. And if our goal is, for example, to detect people on pictures, then neural network will most likely succeed in predicting a person in this picture. So now that we know what is the intuition behind a convolution neural network, the question that arises is that how do CNNs work? Convolutional neural networks, as the name says, are some sort of neural networks that are composed of multiple layers of artificial neurons. And an artificial neuron is a rough imitation of their biological counterparts, as we discussed before, and they are mathematical functions that calculate the weighted sum of multiple inputs and output and activation value. And the behavior of each neuron is basically defined by its weight. When fed with the pixel values, then the artificial neurons of a CNN pick out various visual features. When you input an image into a convolutional neural network, each of its layers generates several activation maps. And activation maps highlights the relevant feature of the image. And we are going to talk about this a bit more. Basically, each of the neurons takes a patch of pixels, a part of the picture as the input, multiply their colors value but its weight, sum them up, and runs them through the activation function. It is in a sense, the functionality is similar to any other machine learning model that you saw. It's more or less getting some input, associating some weight to each feature in the input vector, multiply the weight with the feature, sum them up, and then get a value through an activation function. And in each architecture, that activation function outputs something that means something special for that network. So if I want to give a bit of more, let's say, perspective into the convolutional networks, as you saw, we have several different layers. And the first layer, the bottom layer of a CNN, usually detects basic features such as horizontal, vertical, or diagonal edges. And then the output of the first layer is fed as the input to the next layer, which extracts more complex features such as the corners and combinations of edges. And as you move deeper into the neural network, uh, then the layers starts detecting higher level features as objects, faces, nose, I don't know, whatever. If you look at this picture specifically, as you can see, like the input is a picture of a cat, the first layer feature map retains most of the information present in the picture. You can still say that it is a cat. And basically what is happening here, as I said before, we are just kind of detecting the edges. There are edges here, with different filters. As I said, as we go deeper, the feature map looks less like the original one. For example, here you basically cannot detect whether it is a cat or something else. It is totally unrecognizable. And the reason is that deeper feature maps encode higher level concepts like cat nose or dog ears, while lower level feature maps detect simple edges and shapes. And that is why feature maps, deeper ones, of course, contains less information about the image and more about the class of the image. They still encode useful features, but they are usually less visually interpretable to us. And feature map becomes sparser as we go deeper, meaning that the filters detect less features, and it makes sense because the filters in the first layer detect only simple shapes and every image contain of those, but as we go deeper we start looking for more complex stuff like dog tail that they don't appear in every image. And that's why in the first figure with 8 filters per layer we see more of a feature map as blank as we go deeper to the, for example, this last layer. So now we kind of know what is the strategy, let's say, behind working a convolutional neural network. Now let's see how is their architecture. All CNN models follow a similar architecture, as you can see here. There's an input image that we normally are working on. I mean, as I said, this is like I'm giving the examples only on the images right now, but it is applicable to many other fields. And then we perform a series of convolution plus pooling operations, like here, convolution pooling, and followed by a number of fully connected layers, basically these two. And if we are performing, for example, multi-class classification, then the output is softmax. And probably these things sound a bit abstract for you at the moment, but we're going to go layer by layer and decipher these words. So the main building block of CNNs, as the name suggests, is the convolutional layer. And if you remember from your high school math, or I don't know, the math that you started first years of university, convolution is a mathematical operation to merge two sets of information. In our case, the convolution is applied on the data using a convolution filter to produce a feature map. And there are a lot of terms being used. At the moment, let's visualize them by one by one. On the left here is the input to the convolutional layer. For example, the input image. And I mean, bear with me, it looks nothing like an image, but it is a representation of the image, or this is what we're assuming here. On the right is the convolutional filter. It's also called a kernel. We will use this term interchangeably, so any of them basically means the same thing. This is called a 3x3 convolutional due to the shape of the filter. It is 3x3. We perform the convolution operation by sliding this filter over the input. At every location, look at it here, so basically we put the filter starting from this corner. So at every location we do element-wise matrix multiplication. So 1 by 1, 1 by 0, 1 by 1, 0 by 0, and so on and so forth. And then what we do is that sum up all these results. And then this sum goes into the feature map. Basically, the sum of all these things, we have 1, 1, 1, 1, and the rest are 0. Basically, the sum is 4, and it comes here. And here is what you're seeing in the filter on top left. The output of the convolution operation 4 is shown in the resulting feature map. We then slide the filter in to the right and perform the same operation, adding that result. Basically, this is what you're seeing here. Adding that result to the feature map as well. Okay. Yeah. Okay. This was an example of a convolutional operation shown in 2D using a 3x3 filter. But in reality, these convolutions are performed in 3 dimensions. In reality, in an image, it's represented as a 3D matrix with dimensions of height, width, and depth, where depth corresponds to the color channels, RGB, for example. And a convolution filter has a specific height and width, like 3x3 or 5x5, and by design, it covers the entire depth of its input, so it needs to be 3D as well. So let's have a look at the example. Let's say we have a 32 by 32 by 3. It is not really clear. This is 32 here. This is basically our image. And we want to use a filter 5 by 5 by 3. Note that the depth of the filter and the image should match each other, so both of them are 3. When the filter is at a particular location, it covers a small volume on the input, and we perform the convolution operation as described before. The only difference is that this time we do the sum basically of matrix multiply in 3D instead of 2D, but the result is still a scalar. We slide the filter over the input like before and perform the convolution at each step. Look at this one. It is how it is happening. And to help visualization, we slide the filter over the input as you can see. The thing is that in reality, we could have multiple filters, as you can see here. So there can be 2 different filters working in parallel. The convolution operation for each filter is performed independently, and then the resulting maps, as you're seeing here, are disjoint. Okay, for any kind of neural networks to be powerful, it needs to contain nonlinearity. Both the artificial neural network and autoencoder, for example, there are some types of neural networks. could achieve this by passing the weighted sum of its input through an activation function. And convolutional neural network is also no difference. We again pass the result of a convolutional operation through, in our case, for example, a ReLU activation function. So the values in the final feature map are not actually the sums, but the ReLU functions applied to them. And we have omitted this in the figures that you saw before, but keep it in mind that any type of convolution involves a ReLU operation as well. Okay, so let me introduce another term to you, and that is a stride. And a stride specifies how much we move the convolution filter at each step. And by default, the value is 1, as you can see here, but we can have bigger strides if we want less overlap between the receptive fields. This also makes the the resulting feature map smaller, since we are skipping over potential locations. This is the demonstration of a stride of 2, and as you can see, the feature map is smaller. There is something else that is called padding, and as you see here, the size of the feature map is smaller than the input. Because the convolution filter needs to be contained in the input. If we want to maintain the same dimensionality, we can use padding to surround the input with zeros. As you can see here, the gray area around the input is the padding. We either pad with zeros or the value or other values on the edges. Now that the dimensionality of feature map matches the input. Padding is commonly used in CNN to preserve the size of the feature map, otherwise they would shrink at each layer, which is not desirable. The 3D convolutional figures we saw before also use padding. That is why the height and the width of the feature map was the same as the input, both 32 by 32, and only the depths change. Okay, so we talked about the convolution layer. It's an important layer, but the next important layer here, so we discussed already about convolution, and we want to discuss about pooling. After a convolution operation, we usually perform pooling to reduce the dimensionality. This enables us to reduce the number of parameters, which both shortens the training time and combats the overfitting. Pooling layers downsample basically each feature map independently, reducing the height and the weights, but they keep the depth intact. And the most common type of pooling is max pooling, which just takes the maximum value in the pooling window. So you can see here, this is a pooling window. The maximum value is 6. Here, the maximum value 8. Maximum value is 3. And the maximum value is 4. Note that these windows that we have here and stride configurations have the size of feature map, and this is the main use case of pooling, downsampling the feature map while keeping the important information. Now let's work out the feature map dimension before and after pooling. If the input to the pooling layer has the dimensionality, it's what we have here, 32 by 32 by 10, then using the same pooling parameters as described before, the result will be 16 by 16 by 10. Both the height and the width of the feature map are halved, but the depth doesn't change because pooling works independently on each depth slice the input. By having the height and width, we reduce the number of weights to 1/4 of the input, and considering that we typically deal with millions of weights in CNN architecture, this reduction is a pretty big deal. In CNN architectures, pooling is typically performed with 2 by 2 windows, stride 2, and no padding, while convolution is typically done by 3 by 3 windows, stride 1, and padding. Okay, Let's now consider a convolutional layer ignoring pooling and go over the hyperparameter choices that we need to make. We have four important hyperparameters to decide on. First is the filter size. We typically use 3 by 3, but 5 by 5 or 7 by 7 are also used depending on the application. There are also 1 by 1 filter, which we we don't talk about it here, but at first sight it might look strange, but there are sometimes some interesting application to it. Remember that these filters are 3D and have a depth dimension as well, but since the depth of a filter at a given layer is equal to depth of its input, we omit that. The other hyperparameter is the filter count, and this is the most variable parameter. It's a power of 2, anywhere between 32 and 1024. Using more filters results in a more powerful model, but remember that the more the filters, we risk overfitting to the increased parameter count. Usually we start with a small number of filters at the initial layer and progressively increase the count as we go deeper into the network. The other hyperparameter is stride, and we keep it at default level value 1 normally, and as I said, we usually tend to keep padding. Okay, so we discussed convolution, pooling, and we said we repeat them one after each other. And now we arrive at the fully connected layer. After the convolution plus pooling layer, we add a couple of fully connected layers to wrap up the CNN architecture. And this is the same fully connected artificial neural network architecture that we saw before. Remember that the output of both convolution and pooling layers are 3D volumes, but a fully connected layer expects a 1D vector of numbers, so we flatten the output of the final pooling layer to a vector, and that becomes the input to the fully connected layer. Flattening is simply arranging the 3D volume of numbers into a 1D vector, nothing fancy really. And CNN is trained the same like other artificial neural network, backpropagation, gradient descent. But since it is a bit more mathematically involved, we really don't get into the details of that here. But for now, let's stop here and let's practice a bit and see how we actually can build a convolutional neural network and how we can train the model and predict the results. See you soon in the hands-on practice video for convolutional neural networks.